So we're in 4.7 part 2. So we're going to make compositions of trig functions. We talked a little bit about this when we talked about our inverse functions. So when we came up with the inverse function, we said what was special about a function and its inverse? What do they do with each other? Cancel each other out. They undo each other, right? So what we say is, the way we write that is if we have inverse functions, if we make the composition of the function and its inverse, we talked about this way back at the beginning of the semester, we just get back out x. Whatever we put in, we make a composition, we get the same thing back out. And we can go the other way. If we make the composition of the inverse and its function, we get x back out. Well, with trig functions, it's the same thing, kind of. We have to be careful because we put some restrictions on our trig functions. One, our range of our sine and cosine are between -1 and 1. So our range becomes a domain of our inverse functions. We talked about that. And we restricted the domain of our trig functions. So the range of our inverse functions are restricted. So we can say the same thing as long as we take into account our restrictions. So I'm going to write these rules. We have just a few more rules to deal with when we're doing compositions. So for trig functions, because of our restrictions, we're going to make our list in 3 ways, or in 3 parts. We're going to say the sine of the inverse sine of x equals x, and the inverse sine of the sine of y equals y if we need a couple of things to happen. If x is between -1 and 1. So we have to have between -1 and 1 in our inverse function because no angle has a sine bigger than 1. And y is between minus pi over 2 and pi over 2. So we have to make sure we're putting a number in between -1 and 1 for our inverse function, and what we get out of our inverse function for inverse sine has to be between -pi over 2 and pi over 2. If those conditions are true, then the inverse functions undo each other. If not, then we have to be a little more careful. So let's list our conditions for cosine. So the cosine of the inverse cosine and the inverse cosine of the cosine of y. If, same thing, x has to be between -1 and 1. And what we get out of our inverse cosine is between (0) and pi. That's our restriction for making the inverse cosine function. So we have to put in a number between -1 and 1 into an inverse cosine function, and what we get out of an inverse cosine function has to be between 0 and pi. And then we have one more for tangent. Tangent of the inverse tangent of x equals x, and inverse tangent of y equals y. If, now for the inverse tangent function, I can put in any real number. And our restriction, what we get out of an inverse tangent function, is between negative pi over 2 and pi over 2. So our inverse functions, our function and our inverse functions undo each other as long as these things are true. And if they're not, then we just have to be a little more careful. We have to pick the way we work our problem based on those restrictions. So bottom line, what this is saying is when we're making compositions with trig functions and inverses, we have to pay attention to the restrictions that we put on our functions and their inverses. So questions on this part? What we're going to do next is do a little practice with all of this. So first, review. I just want to review. What is the arc cosine? Just to get us back into the swing of working with these, of negative square root of 3 over 2. And in radians? Inverse trig functions are always in radians? 5 pi over 6. Because the cosine of 5 pi over 6 is negative square root of 3 over 2.
Wait, is it entered in radians or?
In radians.
Oh.
For inverse cosine functions, inverse trig functions, we're always working in radians. So we're thinking this is the angle whose cosine is negative square root of 3 over 2. All right, now let's look at some of these compositions. We want to find the sine of the arc sine of 0.12. So if everything works out well, we can just say this is 0.12. So what we need to plug into our inverse sine function has to be between negative 1 and 1, right? Is this number between negative 1 and 1? Yeah. So these two functions undo each other, and we can just say that's 0.12. So we're good there. How about the tangent, or the arc tangent, of the tangent of 5 pi over 6. We would like to say this is just 5 pi over 6. Can we say that? Got a couple no's. Why can't we say that? It's out of the y range. Y has to be between, our angle has to be between negative pi over 2 and pi over 2. So here's what I'm going to do for this one. Since the 5 pi over 6 is outside what we have to get out of an inverse tangent function, I'm going to do what it says inside the parentheses here. This equals the arc tangent of, what is the tangent of 5 pi over 6? We know that the cosine is negative square root of 3 over 2. So this is the arc tangent of negative square root of 3 over 3. And we figure that out by saying that the sine of 5 pi over 6 is 1/2. The cosine we decided up here is negative square root of 3 over 2. So we get negative 1 over square root of 3, which is negative square root of 3 over 3. Now we can say what angle gives us a tangent of negative square root of 3 over 3 that's between negative pi over 2 and pi over 2. So let me draw a little picture here. You can always go back and visualize our unit circle. There's 5 pi over 6. My cosine, my x-coordinate is the long side of this triangle, and it's negative. Well, where are we going to get an angle here that gives us the long side of the triangle as square root of 3 over 2, and our tangent is going to be negative? The fact that this is negative tells us that we have to be in the fourth quadrant. So I'm going to go down right here to negative pi over 6. The x-coordinate is square root of 3 over 2. The y-coordinate is negative 1/2, and I get my negative tangent. So this is going to be negative pi over 6. Yes?
Would you wrong with that 11 pi?
Yeah, because 11 pi over 6 is larger than pi over 2. So we're always thinking of our fourth quadrant angles as negative angles. Okay? So the arctangent of the tangent of 5 pi over 6 is not 5 pi over 6. It's negative pi over 6. So we have to get out of the inverse tangent function an angle between negative pi over 2 and pi over 2. All right, let's look at another one. The cosine of the arc cosine of 6. Can we say that's 6? Marion says no. Why not? What's that? 6 is too big? I'm saying what angle has a cosine of 6? Does any angle have a cosine of 6? No. So this is no solution. No angle with cosine equal to 6. So this is too big. This is bigger than 1. So this has no solution. Let's look at the inverse cosine of the cosine of 3 pi over 2. Is that 3 pi over 2? Heard a couple of yeses. Does everybody agree? Where does my angle have to be that I get out of the inverse cosine function? Is it pi over 2 to negative pi over 2 for cosine? 0 to pi for cosine. Is 3 pi over 2 between 0 and pi? No, it's clear down on the y-axis. So I'm going to say this is the inverse cosine. What's the cosine of 3 pi over 2? 0. I'm on the negative y-axis. And the inverse cosine of 0 between 0 and pi? Someone said it. What was it? 0. So the inverse cosine of the cosine of 3 pi over 2 is 0. I have to get out an angle between 0 and pi. Let's look at a couple more of these. The sine of the arc sine of pi. Is this pi? Couple no's. A few more no's. Why would this not be pi? What I put into my inverse sine function has to be between negative 1 and 1. Pi is greater than 1. Pi is greater than 1, so this is no solution. No angle has a sine of pi. The cosine of the inverse cosine of square root of 2 over 2? Is it square root of 2 over 2? Heard a couple of yeses. So I'm plugging in a number between -1 and 1 into my inverse cosine. Square root of 2 over 2 is about 0.707. So this is between -1 and 1. So I'm all set. So this is just square root of 2 over 2. So this is one of the nice ones where those two undo each other. Last one. The inverse sine of the sine of 7 pi over 6. Is that going to be 7 pi over 6? Okay. Here's some no's. Why not 7 pi over 6? Has to be, our answer has to be between negative pi over 2 and pi over 2. So I'm going to say this is the inverse sine of, what is the sine of 7 pi over 6? Let me draw my circle here. So here's 7 pi over 6. What's the sine of -1/2? So what's the inverse sine? What angle between negative pi over 2 to pi over 2 has a y coordinate of -1/2? Negative pi 6. So I'm going to be over here on my unit circle. So the inverse sine of the sine of 7 pi over 6 is negative pi over 6. So when we're doing these compositions with functions and their inverses, we have to keep track of the restrictions on what can go into our functions and what can come out of our functions, our domains and our ranges. So questions there? So this is all interesting. Let's make it even more interesting. I hear the cheers already. So for this problem, we're going to find the exact value and before I even write any more, exact value, what does that give us a hint that we're going to be doing? Fractions, radians, or we're going to end up with radicals in our answer, maybe. So this isn't a calculator problem. The exact value of the cosine of the inverse sine of 3/5. All right, so from what we talked about last time and what we've been talking about today, what kind of thing is the inverse sine of 3/5? What do we get out of inverse trig functions? An angle. Who said angle? It's an angle. So this is the angle whose sine is 3/5. And this is the area where I think we were a little weaker on the last quiz. I'm going to call that angle U. Just give it a name. So the angle is U. So what this tells us is that the sine of U is 3/5. So if the inverse sine of 3/5 is this angle U, then the sine of U equals 3/5. This is the angle whose sine is 3/5. What do these two numbers tell us if this is the sine of some angle? That this is the opposite over the hypotenuse. These are two sides of a right triangle. That was, I think, the concept that a lot of us kind of missed on the quiz. This tells us about the sides of a right triangle. So I'm going to draw that right triangle. There's my angle U. Get my eraser here. Here's my right angle. This is the opposite over the hypotenuse. That's 3, and that's 5. It could be the other angle, just as long as you label the sides appropriately. So then if you were up here, then the opposite side would be here. So with this triangle, what's our missing side? 4. This is a 3, 4, 5 triangle. So we're looking for the cosine of this angle, whose sine is 3/5. We're looking for the cosine of u. So what's the cosine of u? 4/5. Isn't that awesome? We have this thing that looks kind of ugly and weird, and we draw this nice right triangle, and we can figure out the cosine of the angle. We can figure out all the other trig functions from this piece of information. So whenever we have our angle, our inverse trig functions or angles written as a number, written as a ratio, that tells us about the sides of a right triangle. And then we can use that information to find the missing part of the right triangle and get the rest of the information we need. So let's look at another one of these, and then we'll make it even more interesting. Any questions here? And let me just write here at the end, just so we make the connection here. So the cosine of the inverse sine of 3/5 is 4/5. U is this angle. This is an angle whose sine is 3/5. All right, let's look at another one of these. We want to find the sine of the inverse tangent of -1/2. So this is the angle whose tangent is u. Or sorry, is -1/2. So we're going to call that angle u. And I'm going to draw my triangle. The tangent of this angle is -1/2. So here's my triangle. Why did I draw my triangle that way? The tangent is -1/2. So that tells me I'm in the fourth quadrant. My angle has to be between -π/2 and π/2. Since the tangent is negative, my triangle has to be in the fourth quadrant. So here's my angle. Which sides of the triangle does this tell me about? Opposite and adjacent. So I'm going to call this one -1 and that one 2. And what's going to be my hypotenuse of this triangle? It's going to be a square root of 5. So c squared equals 2 squared plus -1 squared. So c squared equals 5. So this side is square root of 5. And the sine of u, sine of this angle is what? -1 over square root of 5, and I rationalize that, and I get negative square root of 5 over 5. So the sine of the inverse tangent of -1/2 is negative square root of 5 over 5. And we're in the fourth quadrant, so we know that our sine has to be negative. So we got that part right. Our y-coordinate is negative. Isn't this a cool thing? I love this thing. All right, questions on this process? Let's make it even more interesting now. So for this example, the way that these questions get asked a lot is we want to write the sine of the inverse cosine of x as an algebraic expression in x. So that's how they'll ask you this question. Exactly like what we did before. So this is the angle whose cosine is x. So I'm going to call my angle U. And we know that the cosine of that angle equals x. Now I can draw my triangle. This always tells me about two sides of a right triangle. So here's my angle U. Cosine tells me about which two sides? Adjacent and hypotenuse. So x, what's my hypotenuse? 1. I can think of that as x over 1. And now I can find this missing side. I'll call that B, A, B, and C. So I get b squared, x squared plus b squared equals 1 squared. So from that, b equals the square root of 1 minus x squared. And we want the sine of that angle. So sine of u equals square root of 1 minus x squared, opposite, and my hypotenuse is just 1. So the sine of this angle is square root of 1 minus x squared. So starting with this piece of information, now we know the sine of that angle. If we know x, then we're set. This process is one, it's so fun. I really like it. It's a really cool thing. Two, you use it in calculus. This process, you use it a lot. There's a whole, really a whole section of a chapter devoted to this. We call it trig substitution. And in calculus, usually you're going from this, you're going back the other way to write this as a trig function. So you do the same thing with the triangles, and you turn this into a trig function, because in that case the trig functions are easier to work with than something like this. So we call it trig substitution. You do it a lot. Questions on that? All right, I just want to look at one more of these, just so we see this process again. So we're going to do a tangent this time. The tangent of the arc cosine of 2x. So this is the angle whose cosine is 2x. So I'm going to call my angle u. So cosine u equals 2x. Draw my triangle. This is going to be 2x and 1. This is going to be 2x and 1. And we can find our missing side. Do the same thing. So 2x squared plus b squared equals 1. So b equals the square root of 1 minus 4x squared. And then I can write the tangent of that angle. Tangent of u is the opposite over the adjacent. Square root of 1 minus 4x squared over 2x. Isn't that cool? I just love doing this. It's such a fun thing. All right, questions on that process? Okay, so tonight's homework, just working with these compositions of functions. While you're working, I'll pass your quizzes back. And there you go.